Good morning all. Today we learn the representation of graph into the computer's memory. Means how the graphs are represented into the computer's memory. Actually, there are the three different representations to represent the graph into the computer's memory. The first way is adjacency matrix. The second way is adjacency list, and third way is adjacency multilist representation. So these are the three different ways by which we can represent the graph into the computer's memory. We see one by one. The first is the adjacency matrix. So in case of the adjacency matrix, all of you know that the concept of matrix. What do you mean by matrix? Matrix is nothing but it is the combination of rows and columns. So, in case of the adjacency matrix, suppose here I consider capital G is a directed graph or undirected graph. You can represent directed graph as well as undirected graph with the adjacency matrix. But before going to actual how to represent, first you understand the definition of adjacency matrix. Okay, suppose J is any given graph with the set of vertices and a set of edges. What is capital V? Capital V means the set of vertices, and E is the set of edges. Then the matrix, adjacency matrix is represented with the Aij, that is equal to, you can represent 1 when there is an edge, between the two vertices. There is an edge exists between two vertices, and 0 otherwise. So this is actually the definition of the adjacency matrix. Capital A, that is equal to Aij, is the adjacency matrix. To represent a particular graph into the adjacency matrix, you have to put up either 1 or 0. When you have to put the value 1, the condition is there is an edge exists between the two vertices. Means if there is the edge exists between two vertices, then you represent that edge with the 1. Otherwise 0. Otherwise 0 means if there is no edge between the given two vertices, then you put up the 0. Now I share one of the screen, and you can see the examples of how to represent the particular given graph into the adjacency matrix. Okay, see, actually this is the first way of representation, adjacency matrix. In case of the adjacency matrix, actually I have already told you that adjacency, just 1 minute. Adjacency matrix. This is the example of adjacency matrix. In case of the adjacency matrix, see, this is one of the example. This is the graph, undirected graph. Why it is an undirected graph? Because this graph do not having any particular direction, and that's why this graph is the undirected graph. Just 1 minute. I search the pointer so that you can easily get the particular point or the figure. Just I have to search the spotlight. Okay. See, this is the adjacency matrix, and actually I told you the definition of adjacency matrix, when you have to put up the 1 and when you have to put up the 0. So this is an undirected graph. Why it is an undirected graph? Because in this graph actually no direction is assigned. See, from A to B, only line is present and no any direction is given here. So now you have to learn how this given undirected graph is represented into the adjacency matrix. See, so for that, first of all, you see that there are the total 5 vertices A, B, then C, D, and E. So your matrix is 5 by 5 matrix. See, these are the 5 rows A, B, C, D, E, and these are the 5 columns A, B, C, D, E. Okay. So now you have to make the pairs and then accordingly check whether the edges exist in between that two particular pair of vertices. If it is exists, then you represent that particular edge with the one number, and if edge is not present, then you represent it with the 0. Now we start. See, I start from the first row A and then first column A. So A to A, is there any edge from A to A? No, just like this. See here, for the D node, there is a self loop. Means the A starts from D and ends with the D. So there is no edge from A to A. Therefore, here the 0 is present. Now you check for the second pair, A to B. Okay, see, A to B. Yes, there is the edge present in between the nodes A and B, and hence here the value 1 is present. Why the 1 is present? Because there is the edge exists between A and B. Now the next combination is A and then C. Yes, again in between A and C there is a line, there is a edge, and if the edge exists, then you represent it with the 1. Then check for the next pair, A to D. Again for A to D there is a edge, so again the value 1. Then the next combination, next pair, A to E, and now you see here A to E. There is no direct edge from A to E. You have to go from A to B and B to E. There is no direct edge from A to E, and therefore here the 0 is present. Now after completing, just 1 minute. After completing the first row, you proceed for the second row. Okay, now you check for the B row, B to A. Yes, for B to A, there is a edge because this is an undirected graph. There is no any direction, so you go both way, A to B as well as B to A. The edges exist, so it is represented with 1. Now B to B, no, there is no self loop. There is no any edge starting from B and end with B. Therefore, the value is 0. The next pair is B to C. Okay. Now you check B to C. No, there is no any edge between the vertices B and C, and therefore it is represented with the 0. Now B to D. Okay, B to D. Yes, there is a edge. So B to D, the 1 is present here. Again, you check for B to E, and again the edges exist between the two nodes B and E, and therefore the value 1 is present. So like this, you can check the edges between the pair of two vertices and accordingly put the values either 0 and 1. If the edges exist, then you put the value 1, otherwise you put the value 0. Now we check for the D row. See here for D to D. Why it is 1? Because for D to D there is a self loop. Means this edge is starting from the D and end with the D, and this is called as a self loop. The edge is present for D to D, and therefore the 1 is present here. So this is called as the adjacency matrix. The same adjacency matrix is again for the directed graph. So see, this is a directed graph. Why this is a directed graph? You see the difference. This is the first one is the undirected graph. You see in this undirected graph there is no any direction, but in case of this directed graph, see the directions are placed on the edges. So that's why it is a directed graph. The very similar fashion, you can again make the matrix of the vertices 5 by 5 matrix A, B, C, D, E, and again A, B, C, D, and then you check whether the edges exist or not in between the two vertices. See, A to A, there is no any edge, there is no any self loop, so the 0 is present here. Now the second combination, A to B. Yes, for A to B, there is a edge and therefore here 1 is present. And you check for A to B means there is a outgoing edge from A to B. Then and then you write the 1. Now A to C, yes, again for A to C, from A the outgoing edge is there, A to C, and therefore again here the 1 is present. Now the next combination is A to D. See here, A to D, there is a edge, but from A to D the direction is not assigned. This is a incoming. This line, this edge is not outgoing from A, and that's why from A to D here the 0 is present. And similarly for A to E. A to E, again from A to E there is no direct outgoing edge, and therefore again here the 0 present. So similarly we check for the last node, E node. For E to A, see here in the graph for E node there are only 2 incoming edges. There is no any outgoing edge from the E. म्हणजे E कडे येणारेच फक्त एजेस आहेत, इनकमिंग एजेस, पण E पासून जाणारी कोणतीही एज नाहीये. And that's why here for the E vertices, all the combinations with the other vertices becomes the 0. E to A, no, there is no any edge E to A outgoing, so 0. And similarly for the other nodes, it is a 0. The reason is that there is no any outgoing edge from E to any other nodes. Okay, so this is the first representation, adjacency matrix. Now the second representation is the adjacency list representation. See, this adjacency list representation is most of the time it is also called as the non-sequential representation. The first adjacency matrix is called as the sequential representation of graph. In the second representation, adjacency list, here we use the linked list, and that's why it is called as the non-sequential representation. So in this adjacency list, every vertex of graph contains the list of its adjacent vertices. All of you know that the concept of the adjacent vertices. The adjacent vertex means what? The adjacent vertex means the edge belongs, the same edges belongs to the both nodes. The same edges belong to the every other node, and therefore that vertices are called as the adjacent vertices. Now you see, you clear this concept with this following example. This is a directed graph. Okay, A, B, C, D, E. Again, same figure is here. The 5 vertices A, B, C, D. This is the linked list representation, and that's why here the nodes are used for the all 5 vertices. Okay, this A means information part, and this second part is the link part. That link part consists of the address of next node. Okay, so for A, now you search the adjacent node. Adjacent node म्हणजे काय की त्या नोड पासून जाणाऱ्या edges, outgoing edges. See here, from A there is one outgoing edge to B, so that's why here the adjacent node is B. Again from A there is outgoing edge to the vertex C, and therefore the another adjacent node is C. Now you see for A to D, there is not the outgoing edge. This is the incoming edge. बघा, A to D म्हणजे काय की A पासून D कडे जाणारी कोणतीही आउटगोइंग एज नाहीये, ती A कडे येणारी आहे, म्हणजेच इनकमिंग आहे. सो दॅट्स वाय D इज नॉट अ ऍडजस्टंट नोड. म्हणजे त्या नोड पासून जाणाऱ्या एजेस चे व्हर्टायसेस, these are called as the adjacent vertices. For A there are only 2 outgoing edges, B and C. So B and C are the adjacent node. Now you check for the B node. For B node there are the 2 outgoing edges, E and D. D and E. Therefore, see here the adjacent nodes are D and E. For C, there is only one outgoing edge. Okay, because this is the incoming edge. We consider only the outgoing edges, so only one outgoing edge, and therefore only one adjacent node, and that node is the D node. Now you check for the D. For the D, there are the 3 different outgoing edges. See, this is the first outgoing edge reaches to vertex A. Therefore, A is the adjacent vertex. Then the second one is D. Why D? Because it is a self loop. The edge starts from D and again ends at the same vertex, and this concept is called as the self loop. And therefore, again the D is again its adjacent node, and the third outgoing edge that reaches to the vertex E, and therefore the E is the adjacent node of the D. And what about the E? See here, again E, for E there is no any outgoing edge, and that's why for E there is no any adjacent node. It's a very simple. In adjacency list, you only check the adjacent nodes and just accordingly draw the linked list structure. Okay. So this is the non-sequential representation. You can also represent it with the array. Very simple. Instead of putting that node structure, you just give here the array memory structure. First element of the array always starts with 0. That's why you give the addresses as 0, 1, 2, 3, 4, and accordingly you just write down the adjacent nodes. So this is called as the adjacency array, and this is called as the reference array. The first one is the adjacency list representation using the linked list. Okay, and now the third representation, I will show you here one video. First you watch the video, then I will talk on to that video. Okay, so now you watch the video for the adjacency list as well as the adjacency multi-list representation.
Now let us begin with adjacency list representation of graph. So given a directed graph, let us construct adjacency list for it. This structure consists of a list of all nodes in graph. Since node A has node B and C adjacent to it, therefore adjacency list of A contains B and C. Similarly, adjacent to B are C and D, because of which its adjacency list contains C and D. So every node is in turn linked to its own list that contains the names of all other nodes that are adjacent to it. Note
C. This is the adjacency list representation that we already completed. You have given this directed graph, and according to that directed graph, you just find out the adjacent node. See here, for the A vertex, from A, there are only two outgoing edges. Okay, the first outgoing edge reaches to B vertex, and the second outgoing edge reaches to the vertex C. So that's why the adjacent node of A are B and C. And similarly, search for the other nodes. For B, outgoing edges are towards the C and D, and therefore the adjacent nodes are C and D. For C, there is only one outgoing edge to D, and therefore the adjacent node of C is D. So likewise, you can only
that for a directed graph, the sum of lengths of all adjacency lists is equal to number of edges in graph. Now, we have undirected graph and its adjacency list. Here, the sum of the lengths of all adjacency lists is equal to twice the number of edges in graph. This is because...
Okay. For undirected graph, see how many edges in the graph? 1, 2, 3, 4, 5, 6. But after the representation of this graph into the adjacency list, now you check how many links are there. 1, 2, then 3, 4, 5, then 6, 7, 8, 9, 10, 11, and then 12. And this is the statement. The sum of lengths of adjacency list is equal to twice the number of edges. The number of edges are 6, and here the adjacency list length of the adjacency list are 12. 6 into 2, 12. But in case of the directed graph, these are equal.
Because an edge AB means an edge from node A to B as well as an edge from B to A, because of which it is contained in two adjacency lists. Adjacency lists can also be modified to store weighted graphs. We can see how weights on edges are stored in adjacency list. Here are some key advantages of using an adjacency list. First, moderate number of edges in the computer's memory. Third, adding new nodes in graph is easy and...
Hello.
Hello.
Hello, ma'am.
ओके. कनेक्शन लॉस झालंय. एक मिनिट पुन्हा ट्राय करते मी. Just 1 minute. I share the screen again due to the internet disconnectivity.
The information about an edge of an undirected graph of graph. Firstly, we will understand it with the help of example. Now, we come to version of adjacency list. Adjacency multilist is an edge-based rather than vertex.
Okay. See, this adjacency list representation is a vertex based, but here the adjacency multilist representation is a edge based. Means in this adjacency multilist we consider the edges instead of the vertex, and this is the modified version of adjacency list.
Based representation of graph. Firstly, we will understand it with the help of example. Given an undirected graph, we will construct adjacency multilist for each of the edge. The information about an edge of an undirected graph can be stored using the 5 attributes. First attribute of each adjacency list is intentionally left blank. For adjacency list of H1, H1 is joining vertices 0 and 1. Therefore, second and third field contains 0 and 1. Vertex 0 is incident on H2. Therefore, next field contains an H2. And vertex 1 is incident on H3. So, last field contains an H3. Now, comes to adjacency list of H2. H2 is connected to vertex 0 and 2. Therefore, it contains 0 and 2. Vertex 0 is incident on H1, whose adjacency list we have already seen. Therefore, field 4 contains a null. Vertex 2 is incident on H4, so is the fifth field. Similarly, we can fill adjacency list of remaining edges. Now, when we have seen...
See, in case of the adjacency list representation, we use the vertex, but in case of the adjacency multilist representation, here it is based on the edges, and that's why, see, this is one of the graph which is given to you. This graph is an undirected graph. Okay, this graph consists of the 7 nodes starting from 0 to 6, and the number of edges are 7. So first of all, you have to just label the each box as a edge 1, edge 2, edge 3, edge 4 up to the edge 7. And this edge 1 represents with the 5 different fields. The first field is the M field. That M field is a 1-bit field which represents whether you have to examine the particular edge or not. The second field is the first vertex that edge belongs. Then this is the second vertex. See, for the edge 1, see, this is the E1. For edge 1, the first vertex is 0 and the second vertex is 1. So that's why here 0 and 1. Now, this fourth field is the connection with the first vertex. So you check for the fourth field, the first vertex is the 0 vertex. Now you check which edge is incident on it. म्हणजे इथे तुम्हाला असं चेक करायचं आहे की पहिला
In construction of adjacency multilist, let us look at proper definition of these attributes. Just try to link these definitions with the example we have seen. M indicates whether the edge has been examined or not.
See, this is a 1-bit field and that indicates whether you have to examine the particular edge or not.
Second attribute is a vertex that is connected to Vj by an edge.
This is the first vertex that edge belongs.
Third attribute is a vertex that is connected to Vi by an edge.
This is second vertex.
Fourth attribute is a link that points to...
This is the link I for Vi, means this is the edge which is incident on the first vertex.
Another node that has an edge incident on Vj. Final attribute is a link that points to another node that has an edge incident on Vi.
See, this is the link J for Vi. Link J for Vi means what? This is the link which is incident on the second node. And here just I replay the previous part. Due to the internet connectivity, the explanation is not completed yet. So see here, for the edge 1 means E1, the first vertex is 0. See, this is 0 and this is the second vertex 1. For 0, you have to check which edge is incident on it. म्हणजे 0 vertex साठी कोणती edge त्या 0 vertex ला आलेली आहे तर E2 आलेली आहे. So it is the, just 1 minute, 0 H2. Okay, so this is the H2. Now you
Let us look at proper definition.
now you check for the E1. Now you check for the one vertex. For one vertex, which edge is incident on it? E3. And that's why here E3 is present. Similarly, you check for all the edges.
When we have seen
Second edge is H2. See, this is the H2. H2 is between 0 and 2 vertices. So the first vertex is 0, the second vertex is 2. For 0, there is no any edge incident because already we have visited E2. So it is null. For 2 vertex, you check for the 2 vertex, the another edge which is incident on it, that is E4, and therefore it is EH4. And similarly, you check for the remaining edges, and this is called as the adjacency multilist representation. There is only one difference between the adjacency list and adjacency multilist, and that is only the first field, M-bit field, which is a different than the adjacency list representation. Okay.
Now, given the adjacency multi-list of edges, we can construct adjacency list for vertices. Vertex 0 is in adjacency list for H1 and H2. Therefore, list of edges for vertex 0 contains H1 and H2. List of edges for vertex 1 contains H1 and H3. Similarly, we can get list of edges for all other nodes.
Okay, see. Like the previous adjacency list, we find the adjacent nodes of the given vertex. But in case of the adjacency multilist, see, there are the different 7 vertices starting from 0 to 6. So first of all, you fill 1, 0, 1, 2, 3, 4 up to 6. And list of edges means you just, instead of finding the adjacent vertex, you find the adjacent edge. For 0, there is the 2 edges incident on the 0. Now you check with the diagram. See, again I show you the diagram so that you can easily understand. For 0, edge 1 and 2 are incident. See here, for edge E1, the 2 vertex 0 and 1 are incident. For edge 2, the 2 vertex 0 and 2 are incident on it. So instead of adjacent vertex, in case of the adjacency multilist, you have to check the adjacent edges for all the vertices.
List of edges for all other nodes. Thank you.
Okay. With this, the lecture is over here.